it was a press release that went out through Twitter and so on, so I thought I'd go and have a look at the original paper just to see what the story was all about.
So you do, if people tweet you things, you will look at them?
I will look at them, although this one actually was a tweet from the Royal Astronomical Society because it's their journal that's put the paper out. But yes, no, I look at things when people tweet them to me as well.
All right, go on, what is it?
Okay, so this is a paper entitled A Structure in the Early Universe at Z of order 1.3 that exceeds the homogeneity scale of the RW concordance cosmology. I think that's quite a mouthful for a title.
That is not a catchy title.
It isn't really a catchy title, no, but the physics and the astronomy behind it is rather interesting.
Give me a better title.
The discovery of an implausibly large structure in the universe.
No, that's better. You should have written the title. What's this paper about?
So this is basically a collaboration which are looking at quasars in the universe, so these very bright active nuclei in galaxies, not to study the quasars themselves, but because where there's a quasar, there's a galaxy, so they're a good way of figuring out where galaxies are in the universe, where the galaxies themselves are too faint to see. And they're mapping out these quasars in 3 dimensions to figure out whether they're randomly spread in space or whether they're clustered together, and if they are clustered together, how they're clustered together. So a quasar is a very, very bright nucleus of a galaxy. It's so bright it actually outshines the whole galaxy around it. The picture we have of these things is we believe that pretty much every galaxy has one of these massive black holes in the middle, and probably what's happening where you see a quasar is it just means that that black hole is particularly active, which means stuff is falling into it, which is making it light up. And so when these things were first discovered, they were called quasars because they were called quasi-stellar objects. Which means they look basically like stars because all you see is this very bright nucleus of the galaxy. It's only when you look very carefully you see actually there's a whole galaxy around it. But they're very useful as sort of lighthouses because you can see a quasar at enormous distances all the way across the universe, even if you couldn't see a normal galaxy. So what these people have found is looking at the distribution of quasars in space. They're not randomly distributed. That's not news. But what they've actually found is that they form these incredibly large structures. When you start kind of mapping out the quasars, you find they form these enormous filaments. The latest thing that they found, which this paper is all about, is a structure where the longest dimension of it is fairly elongated, and the longest dimension of this collection of quasars is about 4 billion light years long. And bearing in mind that the entire universe is only about 13 billion light years across, so this is almost a third the size of the universe, this structure. So it's a huge collection of these things.
That sounds like the ultimate elephant in the room. That sounds like it sounds like it's the dominant beast of the universe.
And actually it causes a problem because the picture we have is that when you go to large scales, the universe is supposed to be homogeneous. There's this thing called the cosmological principle that says that one bit of the universe is really very much like another bit of the universe. And of course, if you've got a structure this big, it really means that one bit of the universe isn't very much like another bit of the universe because one bit's got this massive structure in it and another bit hasn't got this massive structure in it. So it actually starts creating some questions about our underlying picture of how cosmology works at all. So here's this structure that they've identified, which, as I say, is about this sort of from end to end here is about 4 billion light years long. And so they've sort of played this game of join the dots. They've found where all the quasars are and found where all their nearest neighbours are and used that to kind of span between them to say, look, it looks like there's a structure here. Now, obviously, you have to be very careful when you're playing this game because if you just threw down a bunch of quasars at random, once in a while they start forming things that look like structures. And so the exercise that you have to go through once you've found something that looks like a structure is say, is this consistent with just kind of a random collection of things and I just happen to have seen them arranged in this way? And the statistics they've done in this paper show that what they found is very unlikely to be just a random distribution of things. It really looks like they found a real structure in that sense. There's a collection of these quasars which are formed into this arrangement of quasars which is not consistent with them just being randomly splattered around the place. The force that we think shapes the large-scale structure of the universe is gravity. It forces things to collapse in certain dimensions, and so actually you end up forming these sort of sheets of things and filaments and those kinds of things, which we've seen all the time. When we look at galaxies in the nearby universe, we find they're not randomly spread. There are some places where there are clusters of galaxies, some places where there are none at all, some places where they form into these sort of sheet-like structures or filament-like structures. So presumably the physics is the same on these scales. What's forming these very large structures is gravity's forcing things to collapse in certain directions. The problem is that that's not what theory predicts, right? The picture we have of the universe says that gravity shouldn't have formed structures on these kinds of scales. So that's why it's starting to challenge our picture of cosmology, is that it seems to be there, but we're struggling a bit to come up with an explanation as to how it might have formed. Which, of course, that's when science starts getting interesting, when you start finding things that you weren't expecting to find.
So is this sort of string of quasars, is there some suggestion that they're all joined by gravity? Are they falling towards each other or away from it? Or is it...
There probably is not. It's not a gravitationally bound structure in that sense. It's just that gravity has started rearranging things. So even though they're all flying apart from each other as the universe expands, the gravity has kind of shaped them into this structure as the universe expands.
Quasars seem like these amazing things, these bright, powerful, violent things. For that reason, are there none in this neck of the woods, or would we know if there was one nearby?
There are no very nearby quasars. And there's two reasons, partly because they're just very rare. So because bear in mind, when you're looking in the distant universe, even a relatively small bit of the sky, you're actually looking at quite a lot of universe. So actually, you're quite likely to find relatively rare objects like quasars. So that's part of the explanation, is that we don't see them very nearby because the bit of space we live in isn't actually that big compared to the things we can see in the distant universe. But the other side of the story seems to be that there was an epoch of quasars that actually, sometime when the universe was about half its present age, there were lots and lots of these quasars very bright in the universe, and then they've sort of died out as we've come towards the present day. And so when we're looking in these objects in the fairly distant universe, of course, we're looking back in time because of the finite speed of light. And that means we're looking back to the epoch where there were lots and lots of quasars, whereas in the nearby universe, they just seem to be dying out, so we don't see so many for that reason as well.
Because the suggestion they're quite rare seems strange to me when there can be a cluster of them that are like a third of the size of the universe.
But bear in mind, this structure actually only contains of order 100 quasars. So it's not like there are billions and billions of quasars in this structure. They're fairly rare objects, but they're just that those that there are seem to be arranged in patterns like this.
You say that this creates problems, and if things flesh out, I know this is early days, maybe it will result in a change of the way of thinking. What would it result in a change? What would change? I don't quite get the problem.
It's partly one of approach, right, in that we had this underlying picture of, well, we want to start creating a cosmological view of the universe, and we start from some fairly basic principles, of which the most basic really is this thing, the cosmological principle, that says one bit of the universe is much like another. And sort of a very direct corollary, a thing that follows directly from that, is that means that you shouldn't have enormous structures spanning large stretches of the universe. So that really means that kind of the philosophy we start from has to change, but also the maths has to change, because we have this picture of the universe based on general relativity that allows us to understand how the structure of the universe evolves with time, how the universe expands with time, and so on. The basic equations we use in those assume that on large scales the universe is distributed uniformly, the mass is kind of spread uniformly, and that allows us to solve the equations. If it turns out that even on the largest scales the mass isn't distributed uniformly, we have to go back to the beginning and solve some much more complicated maths.
You told me that you had a scan of that paper and thought it, at first glance, to you at least, it seemed to check out, and it's obviously been peer reviewed, so there's obviously some merit to that paper. Why aren't you all in the corridors crying and weeping because the whole underlying principle of your careers looks like it's suddenly wrong?
I guess, well, partly because actually that's the most fun piece of science, is when you find something that you thought was to be true actually turns out to be wrong. So it's not really a cause for tears in that sense. But it also, this would be what would be called a paradigm shift, right? That actually things would change so completely. And the nature of paradigm shifts is that you need, the pressure kind of builds up. You need overwhelming evidence. And everyone sort of says, well, okay, that might be right, but, let's put it on hold for now. We'll think about it some more. And then more evidence comes and more evidence comes. Of course, more often than not, you have a piece of evidence and you say, well, we'll put that on one side. And then actually it turns out there was something not quite right with it, or some contradictory evidence comes along. So, but once in a while, this evidence all builds up and builds up and builds up to a point where you have to say, actually, yes, all right, we need to change the way we're looking at things. We're nowhere near that point in this. This is just one of those pieces of evidence. And at this point, it could go either way, right? It could actually turn out there's some flaw in their analysis. It could turn out just to be some kind of statistical fluke. So we just basically need to wait and gather more data, more evidence to say, is where this is pointing actually true, or is there something else going on? And that's the point where, things will really start rocking, things will really change. But at this point, we're just at that kind of, here's an interesting piece of evidence that really doesn't quite fit with our current picture.
Okay.
there's some big structure out there, a long way away from us, and they're saying it's the biggest structure that there is in the universe. Such a large structure is incompatible with a universe which is homogeneous on very large scales. Homogeneous means you're in no special place, that what we see around us is representative of everywhere else in the universe. And so you don't expect, though that the argument goes, I'm not so sure I buy it yet, you don't expect to see such a big structure in a universe that is meant to be, on average, homogeneous.
Let me just deal with a couple of quick things here, Ed. First of all, this term homogeneous. On what scale does homogeneousness kick in? Because obviously there's not going to be Brady's and Eds and rubbish bins and walls and whiteboards everywhere, and there's not planets everywhere. At what level do we start saying things are at this consistency?
That's the big question, Brady. You should be here. So that is the scale. What is the scale above which you would say everything looks fairly uniform, and below which you expect there to be structures? As you said, you and I are quite different in many ways, and then you can just go up. Planets are different, stars, and then galaxies. They're different from one another, and you keep going to bigger and bigger scales. And you think, well, there's nothing homogeneous here. When I look around, things are looking quite different. But the idea is, if you go onto large enough scales, and by large enough, we're really talking on scales of more than 100 megaparsec. A parsec is about 3 light years, so we're talking about 300 million light years. You have to go before you begin to sort of suggest that above that scale, things should start looking very similar, so that when you look at distributions of galaxies and clusters of galaxies and filamentary distributions on those scales, they should look similar from here as they do over here, as they do over there. And what this survey has come in with, it's a bit of analysis of the Sloan Digital Sky Survey, is this massive structure which is kind of shooting right across, way bigger than the hundreds of megaparsecs. So it's up for grabs really as to what you mean by the scale where homogeneity should kick in. People would say 100 megaparsecs, maybe 300 megaparsecs. They're finding a feature on a scale which they say is about 500 megaparsecs. The longest bit of it is 1,000 megaparsecs, over a gigaparsec, but there's shorter pieces. There's a 200 bit here and a 600 bit there. So they've made it into a kind of a volume of 500 megaparsec cubes. And they're saying that is way bigger than, so they've got a structure on this scale, 500 megaparsecs, and that's way bigger than the 200 or 300 megaparsecs, which you would conventionally think of as being the scale of homogeneity. And the big question is whether that is it real? Is it a real feature? I can't really comment on that. I mean, I just find it mind-blowing that the idea you can have 73 quasars linking across a distance of 4 billion light years. It just blows my mind. So how do they determine that they've got this structure? But let's assume it is. Let's assume it's a real structure. The next question is it compatible with an idea that the universe on large scales is homogeneous? It could be that we know there are fluctuations in a universe that's homogeneous. There has to be, because without those fluctuations we wouldn't form. You wouldn't form structures. So it could be that what we're seeing is just a rather extreme fluctuation which is perfectly consistent. And in fact there is a slightly smaller structure that was observed a couple of years ago called the Sloan Great Wall. This was also seen in the Sloan survey. This is a structure of 200 to 300 megaparsecs, so it's not quite as big as this one. And even then, that was pushing the idea of homogeneity. The question was, could you find a structure in a homogeneous universe? Would you expect to find a structure like this? And so some people have been doing numerical simulations. They've been taking a box, putting 100 billion particles in the box, and evolving this box under gravity, assuming the cosmology that we think we have, which is one dominated by a cosmological constant and cold dark matter. And then they're just seeing, and they're putting on top of that, crucially, putting on top of that some small fluctuations. These are the small fluctuations that come out of the inflationary universe. We must do a thing on the inflationary universe, by the way. There's a thing coming out of the inflationary universe, and these are the fluctuations which then grow and seed the structures that we see. And what they find is that they do something like 200 simulations, and they find in 155 of them or something structures of the size that the Sloan Great Wall had. When, the argument at that point was we shouldn't be seeing these structures. And so one question is, if you increase the size of the box that they're doing, will they actually see structures of the size of what I think they've called it, the large quasar group, LQG, huge LQG they've called it. Would they see structures there? And my guess is that they would. You see, the idea of a homogeneous universe with small fluctuations on top works brilliantly. Not only have we got the structures in the universe that we see today, but we've got things like the microwave background, cosmic microwave background, the very small fluctuations in those that WMAP has been measuring. And they released their data on the current status of the universe. They released it on the day the universe was meant to end. Was it December the 21st? So you've got the data of the microwave background, the fluctuations, and that fits beautifully with the idea of a universe which on large scales is homogeneous and isotropic and has these small fluctuations. So it matches lots and lots of data. So for it not to match this data, we'd better have a very good explanation of how the CMB works, for example, if it's not coming out of this kind of model.
There's lots of ifs and buts here on different levels. But the thing that may or may not be under threat is this idea of a homogeneous universe.
Yeah.
Where does that idea come from in the first place? What's that based on? What's this great theory or belief that may or may not be under threat?
It's from Newton. It's fantastic. It's from our local hero, just down the road in Grantham, when he was sat under the apple tree and the apple fell on his head, and he thought, I wonder if this is the same force that's linking the moon going around the Earth and the Earth going around the sun. And that led him to the idea, if it's a uniform force, in other words, the same basic force, then it must be the same everywhere. And so that led him to the idea that we mustn't be in a special place in the universe, that we're just representative. What we see around us is representative of the universe as a whole. And in fact, in his Principia, he wrote effectively wrote down the cosmological principle. That idea that on average, the density of material in the universe is independent of where you are in the universe. It's the same everywhere. That's the idea of homogeneity.
I can see how, if gravity is the same everywhere, this would help create a homogeneous universe. But doesn't that also depend on the distribution of the matter being the same everywhere at
Yeah, that's very good. Yeah, so it does, but on large scales, right? So what we're talking about here, and the model that we're talking about, just to try and put some flesh to these bones, is the universe is very smooth on very large scales. So if I think of the matter distribution in the universe, I think of it as a mill pond, and that matter distribution is perfectly flat. The mill pond's perfectly flat. That's your homogeneous bit. But on top of it, there are these little ripples, right, coming from fish. And some of us are fish. And so these ripples are there. And those are the small fluctuations. So you've got the background, homogeneous, everything's smooth, and then you've got the small fluctuations. And where you've got slight excess fluctuations, that means the gravitational pull. You've got slightly more matter. So from Newton's law, where the force of attraction is proportional to the mass, you've got slightly more here. That will cause things to attract to it. And then it will leave regions where it's attracting matter from. They'll be devoid of matter. They actually will create voids. So you have a natural way of building up structures because of just having these small ripples. Now the question is, from that initial starting point, can you develop the structures that we see today?
Can you make waves that big?
That's right. Can you have the initial fluctuations large enough so that enough matter can collapse in? And this paper is saying, look, we've seen structures on such a large scale that it may be incompatible with that idea of a homogeneous universe with these small random fluctuations. But my gut feeling is that it may not be, that it's actually still compatible. But these are the questions we have to ask and try and answer, and that's what we'll do with numerical simulations and with more analytic approaches to try and do it.
In that analogy you made with the fish or whatever it was making little ripples on our mill pond, what's the reality in the real universe? What's causing these fluctuations that allow large structures to form?
Okay, so this is where it gets really fun. All right, now we're moving back to the very early universe. How early? About 10 to the minus 35 seconds into the universe. That's really 34 zeros and a 1, okay? Seconds into the universe. And this is the period known as where the universe expanded exponentially quickly. And so the space expanded exponentially rapidly. And in that universe was a thing called a scalar field, a bit like the Higgs field, permeating the whole of the universe. And it fluctuated because of quantum mechanics, just like the Higgs field fluctuates. Randomly. And those fluctuations, the big difference that goes on here is that those fluctuations don't just remain small. Because the universe is expanding so rapidly, they quickly get they're grabbed hold of. I'm getting too excited. I'm speaking too quick. Slow down.
Ed, I will never accuse you of speaking too quickly.
These fluctuations get grabbed hold of by the expansion of the universe and stretched onto big scales, and those are the cosmological scales, and it's there that the initial seeds came from. So what we're seeing when we look at the large-scale structures in the universe, when we look at the microwave background fluctuations in the W map and see these hot and cold spots, what you're actually seeing is an imprint of those very early moments, way before a microsecond, way before a nanosecond into the universe's history, when these fluctuations from the field emerged.
A big blown up projection of just a funny little wobble in a field.
Wow, exactly. You know how to say things scientifically, technically correct.